Our fourth individual presentation is in the area of computer science. Armand Bilge is from the Lexington High School in Massachusetts. His mentor is Miss Yi-Chi Wu, a research assistant at the MIT in Massachusetts. Armand.
Thank you, Professor. Hi. So organism interactions are extremely important to life. We observe them across the biological domain, and they have so much significance to biological processes. We observe them in animals. We see pollination mutualisms. We see parasitisms. We also see them on microscopic scales. We have bacteria in our gut that enable us to digest our food, and there's viruses which attack cells, which attack bacteria. So one of the big questions in biology is, how do these sorts of interactions evolve? And once these interactions have emerged, how does the evolution of one organism affect the evolution of its partner? How does the fact that they engage in a symbiotic interaction affect their evolution? One of the model organisms that's been considered a lot in this regard are gophers and lice. Obviously, these are parasites. I haven't heard of nice lice. And so whenever you have an evolutionary question, the way you address it is with phylogenetic trees, or creating family trees of the organism, because these trees represent evolutionary processes. So it turns out we're very good at doing this using the organism's DNA sequences because it's been so well studied. It's excellent. We have a tree for a gopher. We have a tree for a louse. But obviously, the next step is we want to compare the two trees to each other. We want to see how the associations between the individual species gives us insight to the coevolutionary processes. So we can put the trees next to each other like this. Hafner and Adler did this in 1988. And now we can see some patterns beginning to emerge. There's some correlation between the two trees. But there's also differences, especially on a finer scale. So that means that coevolution must be a complex process. The trees don't match exactly. It's not just two organisms evolving exactly the same way. And so really we're interested in a diagram that looks something like this, where we placed the tree of the evolutionary history of the symbiont, or the louse, on top of that of the gopher. And so I made this using one of the tools available today. And now we have biological events that can explain the differences we observe between the two trees. So, for example, we have here a host switch event where the where the louse speciates and switches to a new gopher host. We also have events such as duplication, where the louse speciates and remains on the same host. And finally, there's the simplest event, which is co-speciation, which is when the louse and the gopher speciate together. But here's the catch. If I change the parameters I used to generate this, we get a completely different explanation for the two histories of the organisms. In this one, we see a new type of event, which is an extinction event. The louse went extinct on this particular lineage of gopher. And the result of what we see is that by making a small assumption in the parameters used, we can get totally different results. And so the other assumption we made here is that the trees that I provided are perfect trees. And that's not really how it works. What happens is we have some degree of confidence in the tree based on the data, and we want to consider that in the analysis. And the way we reflect uncertainty in science is using probability. And so many other evolutionary processes have been brought to probabilistic methods. Like, for example, molecular evolution, how DNA mutates, has been brought to probability. Biogeography, how an organism speciates and spreads throughout a geographic area. All of these have been brought to probability. And the reason I display it as a puzzle is because once a model is probabilistic, it plays well with the other models. You can start to combine them and use them alongside each other for bigger analyses. So is coevolution next? Can we bring coevolution to this probabilistic framework? And so to start doing this, I said, okay, we need to know the probability of a complete coevolutionary reconstruction. So that involves a host tree, the symbiont tree, and the reconciliation, or sort of the overlap, how the two trees fall on top of each other. So using Bayes' theorem, we can actually split this into two terms, a likelihood and a prior. The other thing that I want to emphasize here is we have this parameter theta, and theta represents the rates at which these events occur. the rate at which host switches happen, the rate at which extinctions happen. And by integrating or trying all these rates, we're avoiding making an assumption. I avoid making an assumption about the rates and affecting the results we get. And so we can consider first the likelihood term. So the likelihood term actually breaks down and simplifies into the likelihood of the host's evolutionary history and the symbiont's evolutionary history, or the probability of observing the DNA sequences under those, for those evolutionary histories. And we already know how to address this. This problem has been solved. So the likelihood is not a problem. So then we look at the prior. The prior can also be split into two terms and finally simplified. One of them, one half of it is very easy. We already know how to address these, or it's simple to come up with methods. But the key term is this one. It's the probability of observing the symbiont's evolutionary history given the evolutionary history of its host, the mapping between the two trees, and the rates for these coevolutionary processes. So it turns out that it's hard to calculate this particular term. The reason is because there are unobserved events that can happen. For example, there could be 100 duplication events of the symbiont, but all those lineages go extinct. So we end up not observing any result from their process. So instead, I make an approximation by considering just the events that we observe in my model. So then we end up with the rates of observing these particular events, which I treat as independent Poisson processes. That means that they have independent rates which dictate how likely a particular scenario is. The only one that I treat differently from the host switch, duplication, and extinction is co-speciation. Because co-speciation can only occur when both speciate at the same time, I assume that occurs whenever the host speciates, the symbiont speciates as well. So I developed an algorithm to approximate this particular term, and when you consider only the observed events, it turns out that there's just 7 cases that are possible, and any uncertainties can be integrated out, or basically all situations can be considered when doing this calculation. So these are the 7 cases that it falls into. Some of them are fairly simple, like this one is simply a duplication of the symbiont, or this one's simply a host switch. But we can also look at more complex cases. I'll discuss this one in detail. So in this case, what we observe is a symbiont on a host, and it speciates and host switches to a new host, and then it speciates and host switches yet again to another host, and finally it goes extinct. The original lineage goes extinct. So that means that today we're left with this particular symbiont and this particular symbiont. So when we reconstruct the phylogeny, the evolutionary history of them, we get the time of their most recent common ancestor. And that goes back over here to the time of the first host switch. So excellent, we know when the first host switch occurred. But the problem is we do not know when the second host switch occurred. So we can just integrate or try all the possibilities, consider all the possibilities. So we're just integrating, not a problem. But consider if down here the host lineage speciated. So in order to explain this currently, we would need to have an extinction event occurring here on the symbiont. But as we continue integrating, as we continue moving the host switch later and later in time, then that particular event goes away. So depending on when the host switch occurs, the events can differ. And so there's these subtleties to the cases that need to be considered. So after developing this algorithm, I implemented it in a larger model which reconstructs the complete coevolutionary reconstruction. And we can actually determine this analytically. So instead, we need to approximate it using, again, a computational technique, uses Markov chain Monte Carlo. What this does is it starts with a random guess of the host tree, a random guess of the symbiont tree, a random guess of how they fit together, and it takes a random walk to explore all the different possibilities and explore how they fit together. I implemented my particular algorithm inside Beast, which is an existing package for these evolutionary analyses, and it already uses these Bayesian MC techniques. Finally, I set it up so that in the analysis, all parameters are estimated at the same time, including the host tree, the symbiont tree, and the mapping between them, so that no assumptions are being made. We don't need to assume anything for a particular analysis. I did some simulations to test how well my algorithm works. The first simulation was fairly simple. I set the duplication, host switch, and loss rates all to 0 to make perfectly matching trees, and the estimated median rates from those analyses were very low. For the second simulation, I set the rates all equal to 1. And again, the estimated median rates from the MC analysis were in the ballpark, but in both cases, the rates were slightly higher than the actual rates used for the simulation. This should not be a surprise, because in these Bayesian MCMC analysis, during the random walk, both simple models and more complex models need to be considered, and the more complex models would be driving up the rates. And this is a known artifact of these Bayesian MCMC analyses. The other interesting result that I got are these symbiote trees. So these symbiote trees perfectly match those generated during simulation. The values at each of the ancestral symbiont nodes represent the probability that it was reconciled to its original host during the simulation, during the analysis. For the simple one, for the most part, it was perfect results. However, for the more complex model, some of the nodes were reconciled to the original host the majority of the time, but other nodes had more trouble. Probably the reason for this is because these were fairly small simulations using about 8 taxa for both the host and the symbiont. And as a result, there might not have been enough data to properly train the parameters, to properly estimate the parameters. But potentially for larger data sets, there will be more success in reconciling the host and the symbiont trees. So the main contributions I did were I formulated a Bayesian expression for coevolutionary reconstructions, and in particular priced out the term for the probability of the symbiont tree given the entire reconstruction, and I developed an algorithm that we can approximate it with. Finally, I implemented that algorithm in an existing package for phylogenetic analysis, such that biologists can start using this tool today. There's a lot of opportunity for future work. Obviously, I want to start looking at real data sets, such as the gopher and last data set that I showed you. I became interested in this project because of a plant-beetle pollination mutualism, and I want to apply this work to that data set. There's also preferential host switching, which is an interesting thing that can be included into the model. For example, we see HIV switches. There's 2 types of HIV coming from chimpanzee and monkeys, and that coming from chimpanzees is more virulent because chimpanzees are more closely related to people. I showed the puzzle, so we can integrate my model with the biogeography, with the geography model, since the host and symbiont must be living in the same place. And finally, there's a lot of coevolutionary theories in the literature that we can potentially test using my work. Find a lot of acknowledgments. Mainly, I guess I want to highlight that my mentors, when I started, there were 2 graduate students and a postdoc. Now one is a professor. Now it's Dr. Jessica Wu. She defended last week. So that's very exciting. And, of course, thanks to a lot of people who helped, my family, Siemens Foundation College Board, and George Washington University for bringing me here, for giving me a stage as well.